Hey everyone, class is not over. It's time. Who's all here? Let me go in. Maybe I'll drop right here. And there we go. Hey John, what's up? You ready to do some work? Let's pop out the chat. Reptar's here. Krish is here. We got a bunch of people here. We're going to do some work. Should we do the homework first? Complete the full homework? What do you think? What do you want to do? It's your time. It's our time here, right? It's our time. So let's say the quiz. Okay, chapter 12 or office hours live, chapter 12. Look here. Which quiz question are you working on? Name the quiz question, we will do it. Name the quiz question and we will do it. There we go. Got that going. Ma Pearson. It is a beautiful day out. It is just... You have to go on a little bit of a walk. You have to go outside. You got to see the world. That's what the world's about. Which quiz questions shall we do? There's a lot of quiz questions. That's why sometimes I do the homework first. Hey, Brock, good to see you there. What'd I do wrong? That's my password. Anyone put a question in, we'll do it. This is our time here. So you drop in the questions, we'll do it. So you drop the questions, we do it. Lily, good to see you there too. And here's, oh no. I could go find, okay, I have it open. Okay. Want you to take a while for me too. Chapter 12. Chapter 12 is a fun one. I love chapter 12. Please question, I could just start doing all of them. There's a lot though. We can get through most of them. Anyone have a question? No worries. No worries. Get some easier ones, some more difficult ones. Drop a question. Which question are you working on? You say, Brian, do this question. I'm working on this question. Help me with this question. Which question do people have? You're in? Nice. I'm in too. Which one? Anyone, any question. You can say, do the homework, do the quiz, do this question. The quiz has a bunch of questions, so you have to be like, my question says this at the start. So we have it up. Here. Go to main screen. Which one we gonna do? I could do some of the difficult ones. Let me go grab a difficult one. We'll do one people find difficult. This one. A nervous kicker. Okay, let's do nervous kicker. A nervous kicker. Just drop the questions you have and we will do as many as we can. The car ones trick people up too. A nervous kicker. A nervous kicker. Drop the next one because this one will be pretty quick. You'll be shocked to be like, no way. Reptar's loaded in. Okay. Stat 201, chapter 12 quiz. A nervous kicker. So what you want to do, especially for these later chapters, is you really want to know your notation, as Leo said.
Notation, brother.
About that notation, brother. So a nervous kicker has a 80% probability of making a kick. So what we would do right here is we'd write down probability of good kick is equal to 0.80. So if he makes his first attempt, his next attempt is a probability of 94%. What is the probability he makes his first two kicks? So he makes his first, and then he makes his second. When I say and right here, the probability actually does change because it's dependent, but it gives you the new probability. So this is good one first kick, and then probability of good second kick is equal to 0.94. So it actually gives the probability of the first kick being good and then the second kick being good. And notice the and right here. Now, I know this does not pass the rule of multiplication, but rule of multiplication says that the probability doesn't change between, but this one gives a different probability because it's saying the probability updates. Like, he makes a good kick and he's like, oh, I got this. So all we do is multiply right here. So we could take... trying to do it in my head. So that'd be 18, 1, or I'll just do the calculator. Let's just do it. 0.80 times 0.94, and there it is. There's the math. And we drop it in, and problem is done. Okay. It is the probability he makes the first, and then he makes the second to figure out the probability of making two kicks in a row. Given these probabilities, the probability he makes the first is 80%. So probability good first kick is 80%, and probability kick second good kick. You're welcome, Brock. Next one. What's the next question? That is how that one is done right there. It's not doing the direct rule multiplication. It's showing you a new probability that has kind of changed because the new probability updates, which the rule multiplication would be each kick needs to be independent of each other kick, which they're kind of not. We could do the soda one while we wait for more questions. It's one of my favorite ones, the soda question, the sales promotion. I love this question. Oh, wait, John's got one. The probability is that an adult male has high blood pressure. Okay, it might have been this one. Here we go. I think this is it. Oh, man, John, we found it. Number 24. Okay. So we're going to put this one in, drop more questions. Remember, everyone, I do whatever questions you ask for. So if you're watching this and you don't get the question, just drop it and we'll do it. Okay, so this gives probabilities of people and high blood pressure and things like that. So you can see right here, many ways that this could happen is, like, where do you want to be? I mean, as long as you want to be what I want to be. Do you want to be up here, top left, top right, bottom left, bottom right? Where do you want to be? Explain to me what's going on with this. Where do you want to be? Where do you want to be? Where do you want to be? Bottom right, yeah. Unless you're like, man, I really love some high cholesterol. You're like, man, I want to eat all those I mean, you get to eat cheeseburgers then, right? Maybe. But probably won't be down there. So this is probably where we want to be, in the region of okay cholesterol and okay blood pressure. Okay. And so when we look at the problems that ask right here, it says the probability that a man has both conditions. Now that one's nice and easy because we can just go right here, and I'll disappear for a second. The probability of having both conditions is 0.14. So that's just going to be the probability right here of 0.14, the probability of both conditions. Next one says the probability that a man has high blood pressure is this. So a certain bowler, you got it. We'll do the bowler one next. That one's a little bit longer. You got it, Lily, though. So the probability was a high blood pressure. I think it was high blood pressure is going to be actually the addition rule, because high blood pressure is going to be adding up both of these right here. So that's the addition rule. The addition rule says that we can add up probabilities that are mutually exclusive. So you've got someone who has high blood pressure and high cholesterol, and someone who has high blood pressure but okay cholesterol. These people don't overlap because they're mutually exclusive. You can't have high blood pressure, okay cholesterol, and you can't have high blood pressure, high cholesterol. So we can add together these probabilities and get 31%. That is the rule of addition coming into play right there, that you can add together probabilities that are mutually exclusive. Make sure you know what mutually exclusive is. If one happens, the other can't happen. Kind of like you can't make an A in a class and also B in that same class that same semester. The probability that a man with high blood pressure has high cholesterol. So with high blood pressure has high cholesterol. Okay? With high blood pressure has high cholesterol. So now we need to look at within here. The probability of a man with high blood pressure having high cholesterol. Well, this is a total of 31%. And then has high cholesterol is going to be this. So we get 0.14 out of 0.31. So it's going to be that right there, which is a little bit less than 50%, like 46 or something. 0.14 divided by 0.31, and there it is right there. So that is the probability, and I think it wants it as decimals. We'll double check. And so it does want it to 3 decimals. The other ones did not have 3 decimals. Ooh, got another one from Reptar right there. The probability that a man has high blood pressure, if it's known, I'm going to double check. The probability that a man has high blood pressure, the probability that a man with high blood pressure has high cholesterol. Now this one says the probability that a man, let me make sure I get this right. The probability that a man has high blood pressure, okay, if it's known he has high cholesterol. They're totally flipping the wording. If it's known he has high cholesterol, then it's known he has high cholesterol. And the probability of him having high blood pressure is going to be this. So now we have to take the denominator, really, and do this. What's up, randomize? We got the internet's back. We got the Ma Pearson's back. There we go. That's how that one's going to solve out, because it's out of that total. Bottom right, okay, you bet. That's the best spot to be. And so it's 0.14 divided by 0.39. We should be okay on this. Not one of my favorite questions. I don't think it really reviews the chapter really well. Got it right? There we go. Okay, we got the next one right here. The bowling question, I believe. Let's go find the bowling one. I like the bowling one a lot. Those are my favorite. Okay, here we go. Found the bowling one. A certain bowler. Okay. We were just rocking and rolling through these. Drop your questions in the chat. We will do as many as we can. Probably getting in around 210 or so. So we got like 55 minutes. We're going to get so many done. We probably do all of these. So if you drop your question now, it's likely we will get to it. So drop the question, and if I miss it, be like, Brian, you didn't do this one. And then if another person gives the same question, we'll circle back around later. But we'll try to do new questions, as many as we can. Okay, so what does this boil down to in later chapters? You need to know
Notation, brother.
And by that I mean, I'm going to write right here, and I want you to put in the chat for some points. How am I going to mark this as notation? What am I going to mark? I can write two things out right now. What can I write in notation? So we're looking at the probability of a strike is 80%. How do I write that? How do I write that? And bowling looks like this. No, it's not bowling. How do I write probability of a strike is 80%? Kind of. That would be true probability or true proportion. For this chapter, and a little confusing, we do, and gosh, I wish I had the notes up. Lily, points in the chat. Probability of strike is equal to 80%. And the notes also show this. The chapter, the formula sheet shows it. Probability of not strike is equal to 20%. Does that make sense right there? Where P is true probability from what we did today, and P hat is sample proportion, or true proportion, sample proportion. Slightly similar-esque, but little, small, minute differences.
Little bits.
The probability of going 2 consecutive frames without a strike. So what would you do if you went 2 consecutive frames without a strike? What would happen down here? If you think about a strike as yellow and not a strike as red, what would happen? Like, explain to me what happens. You're a great bowler. You get 80% strikes. So what happens? What happens if you go 2 consecutive frames without a strike? What would happen? Just tell me. Just like, what happened? What'd you see? What happened and then what happened? Notice the and. 2 consecutive frames without a strike. Here's what happened, but tell me about it. It just happened. So what happened? And then you'll see there was not a strike and not a strike. So what's the math? There was not a strike and not a strike. So what's the math? I'm gonna have people solve. I'll do the next one. I'll do the next one. I'll completely do the next one. Boom, you got it. 0.2 times 0.2. So it's gonna be 0.04. But the math on this one's going to be not strike times not strike equals 0.2 times 0.2, which is 0.04. It should be 0.04. The next one says the probability of her making her first strike in the second frame. Ooh, Peyton's got a good one right there. So first strike in the second frame would be the following. She would have to go not a strike here. Does that make sense? Like she goes not a strike, and then she gets a strike. So we know the pattern has to be not a strike and then a strike. So not a strike and then a strike goes 0.2 times 0.8 equals 0.16. Who follows me on that? Because if you get your first strike in the second frame, there's 10 frames in bowling. So you had not a strike and then a strike. Exactly. And the next one says probability of having at least one strike in the first 2 frames. I know the answer. Who knows? Can anyone tell me for 5,000 points, what's the probability of having at least one strike in the first 2 frames? And then how'd I know it? Take a moment and see if anyone can figure it out. The probability of at least one strike is easy to calculate because we kind of did it. You'll either get at least one strike, right? Does everyone agree? There's the first 2 frames. You have at least one strike. So you'll either get at least one strike, that's at least one strike, or you'll get how many strikes? Does everyone hear that? You'll either get at least one strike in the first 2 frames, like you got it in the first frame, but you didn't get it in the second. You'll either get at least one strike, or you'll get no strikes. So you're either going to get, I want to zoom out here a little bit. Can I do it down here? No, I can't. Okay. You either get at least one, or no strikes, which means 1 minus no strikes, because you can just math this over to the other side, is the probability of at least one. 1 minus no strikes, which we already did no strikes. We already did the probability of no strikes. So 1 minus no strikes. So 1 minus no strikes equals at least one strike. Because when you think about it, you're either going to get no strikes, there's 2 no strikes, or you're not going to get a strike first, not get a strike second. So of everything that can occur, there's only 4 possibilities. Who follows me on this? I think, John, you see it, that this is the sample space of what can occur. And so if you think about this has to equal to 1, everything right here, no worries, randomized, I was wondering. One of these things must occur, and you can just subtract this off to get the probability of at least one strike. Because that's, in our color coding of yellow, that's at least one strike right there. So 1 minus no strikes is at least one strike. It's the complement of no strikes, it's at least one strike. And we already have the probability of no strikes, so we just do 1 minus this, and that's the answer of 0.96. What is the probability of a perfect game? A perfect game is 12 strikes. So you have to get 12 strikes in a row. So it's simply this. It's 0.8 to the 12th power. I hope this helps people out. I think there's different versions of this. 4, 16, 96, and crazy number. 4, 16, 96, and then 0.8, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There we go. And then what does it want it to? How many decimals? Thousandths. So 10th, 100th, thousandths right here. And then we check answer. Oh no! What'd I do wrong? The probability of her making literally right here at the start. Didn't put a 0. There we go. Math errors. I'd probably give that back if you emailed me and said, hey, Brian, I forgot a 0. I'd be like, okay, that makes sense. Okay, that one was a little bit longer. It's a really good question, though. We did the blood pressure. Now we have a 2015 National Center health statistics. Okay. A 2015 National Center. The landline, no landline one. That's an interesting one. The Red Cross and Mars are interesting, too. Where is that landline one? The landline. Here's the landline one. Oh. So with this landline one, what are we going to note first about the probability of someone having a landline? And I just call this the probability of having a landline. I know it says and no cell phone. It says 71% of people had a cell phone. So we're going to call this the probability of having a cell phone. It says and no landline, but we're just going to ignore that. So this is going to be the probability of a cell phone. So we're going to take this right here. We're going to ignore where it says a landline because that's just like extra wording. And we're going to write what? What do you think I'm going to write? How am I going to... We'll do Mars. Mars is a good one. What do you think I'm going to write for this? How do you think I'm going to summarize that? And that's kind of similar to Peyton's a little bit. Yes, Peyton. Yeah, and tell me, Peyton, you got the next one. If this is not yours, like, be like, can you do the other one? Because I see Peyton also has. This is similar-esque, but I don't know if it'll solve the previous one. So we're gonna write very close, Peyton. We're gonna write probability of cell phone is equal to 0.71, and then we'd write probability of no cell phone is equal to 0.29. So we have the event and we have the events, or we have the outcome and the outcomes complement. What is the probability that all of these adults only have a cell phone? Which only having a cell phone is this probability right here. And they all have a cell phone, and we're talking to how many people? So we're talking to 9. So what is the probability that 9 people all have a cell phone? Who's got that? What is the probability the first person has a cell phone, and the second person has a cell phone, and the third person, you notice I'm saying and for the multiplication rule. What is the probability the first person has a cell phone, and the second person has a cell phone, and the third person has a cell phone? That's exactly it, Peyton. Yep, you take 0.71 to the 9th power, and you hope they're all independent of each other because it can't be a family, because then the probabilities would be related. What is the probability that none of them have a cell phone? So the first one doesn't have a cell phone, and the second one doesn't have a cell phone, and the third one doesn't have a cell phone, and the fourth one does not have a cell phone. So what's the probability the first one doesn't, and the second one doesn't, and the third one doesn't, and the fourth one doesn't, and the fifth one doesn't? What's the probability of that? What's the probability of that? Exactly. It's just the complement raised to, I forgot to put the timestamp on this one, but it's just the complement raised to it. So you just do the complement. You just do 0.29 raised to the ninth. Whatever it is, it says 9. So that's very important. That's why we're doing the 9s right there. What is the probability at least one of these adults has a cell phone? So now you have to think. It's either the case at least one has a cell phone. So that's at least one has cell phone. Or what? It's either the case that at least one has a cell phone, which is, now we need to figure out what other would be the thing. Either at least one, imagine you run around. Does anyone have a cell phone? Either at least one person's going to have a cell phone or what? Either at least one person's going to have a cell phone or what? Maybe they all have cell phones. So either at least one person's going to have a cell phone or what? Or none, exactly, or no one has. So it's either going to be the case that at least one person has a cell phone or no one has a cell phone. Does that, you have to write this sentence. That really helps out because once you write this sentence, you can take and bring this to the other side, and then you do 1 minus no one has. So what is the, and we're trying to find at least one has. So this is the thing we're trying to figure out, at least one has. And I think Reptar might have it right there. Let's see. None of them, exactly. Because this probability no one have a cell phone is right here. We figured out the first person doesn't, the second person doesn't. You just do 1 minus that, and that'll get you the probability at least one has. Yeah, that's it. Once you figure out how to solve these at least one problems, it's all about writing the sentence and then just flipping it. So you have to be like, well, either at least one has a cell phone or no one has a cell phone, and then it's like one of those things must happen. Like that's what one means, is like one is something must occur. So it's going to be 1 minus, disappear so I can write it. Great job. The quicker we go, the more we can do. I like that. 1 minus 0.29 to the 9th power, which is going to be a big number. So 0.29, 2, 3, 4, 5, 6, 7, 8, 9. Is that right? Holy mackerel. How many decimals does it want on this? That's 0.000. Oh my gosh. 5 decimals. So I'm pretty sure this one is 0.00001, making this one 0.9999. And then this one was the 71%. So 2, 3, 4, 5, 6, 7, 8, 9. There we go. I think we did it right. Then the 5 decimals, 1, 2, 3, 4, 5, and I don't even think it has leeway on this. I don't think it has leeway. I think it's very mean. Yeah, you got to be very exact on this one. So be very, very careful. You can put it in Google too. Like you can have Google solve the math, but if you do 1 decimal place error, like I just showed, it gets mad. It's very exact. It's perfect math. So you can drop that into Google right there though. Like Reptar's done. If you take this equation and just Google it, Google will calculate or solve it for you. Let's bring up. Google's weird. What? Well, I was wrong. You can't Google it. Google gets mad. Let me try Google it again. Maybe it's because of the. It doesn't do it. That does it. And then copy it and paste it in 1 minus. But I was like Googling it and it didn't do it. Okay. Well, let's do the next one. Peyton, did that, yes or no, Peyton? Is the other one, do you want to do the other one? Or this one's basically the same, isn't it? Very much. That one's easy. Those are easy ones. We can do it if you want. There's some easier ones. We'll see what Peyton says, and then I think we'll do John's question here, the Mars Candy Company. Numbers are wrong on yours? If you want Peyton, drop your numbers. I can go back and check it out. Here's the Mars one. This is a longer one. We'll do it here. The Mars Candy Company. The Mars Company. Promoting Mars here. I got to get candy for tomorrow. Do an event. Okay. Let's do this one. Okay, we're going to need a sheet of paper for this one. So here we are. In this problem, you are told the makeup of how M&Ms are. So what we need to do, got another question, I think, is we need to write this all down. Ooh, I should go check out Costco. My wife and I need a membership. We're thinking about doing it for Christmas. So we see that before introducing purple, the candies are either yellow, red, orange, blue, green, and brown. It might be that, Peyton. That sounds about right. If the probability of a landline is 0.51, that the probability they all have landlines is 0.51 to the 6 if it's 6. Yeah, sounds about right, Peyton. And with this right here, what I do sometimes is I draw a table. So we have the event and the probability of the event. So we have what is an event? When you pick up an M&M, what is an event? It could be what? What is an event right here? When you pick up an M&M, it could be what? What is an event? You pick up an M&M, and it could be what? You can start at the beginning. And you have to make sure I get this table right, because I have messed it up, and it messes up the whole question. So if you see errors, let me know. What's a possible event? What's a possible event that it could occur when you pick up an M&M before purple? What's a possible event? It's blue. So we'll start here with red. And red is a possible event, which has a probability of 20%. And yellow is a possible event with a probability of 20%. And then orange, blue, and green. Orange, blue, green, all are 10%. Now, for this to be a valid distribution, a valid probability, what must this add up to? If this is valid probabilities, orange, blue, green, I think we've done it. If this is valid probabilities, must add up to 1. So what's the probability of a brown M&M? Because the rest are brown. So what's the probability of a brown M&M? Figure it out. Because if it's a valid sample space, exactly, John. If it's a valid sample space, it has to add up to 100%. And the math, we just add up. My 3s look horrible. Look at that 3. No, that's all right. You got the math and now randomized. You're here. You got this. You're morbed in. So we see right there that it is 30% because now if you add everything up, the sum of the probabilities is equal to 1. So we've got the mathin'. We like this. So what we do is we look at the question, and I'm going to put these both on the screen at the same time. One moment here. Okie dokie. And here's the question on the screen at the same time. Okay, and I'll disappear. Okay. What is the probability the M&M is orange? Well, it literally says that. Who follows me? Like, this literally shows the probability it's orange. The probability it's orange is 10%. What is the probability it's brown or red? What rule are they using to say brown or red? What rule are they using to say brown or red? Notice it says brown or red. So what rule are they using to say brown or red? What rule are they using? The addition rule. And do note that you can't get a brown or red M&M, meaning that this is what of each other. You can't get a brown or red M&M at the same time, meaning these two things are what of each other. I'm going over here to show you this. You can't get a brown or red M&M at the same time, meaning these two things are what of each other. You can't get a brown or red M&M at the same time, meaning these two things are what of each other. Answer in the chat. You can't get a brown or red M&M at the same time, meaning they are what of each other. Exclusive. Now be careful though. Remember when we say or, and mutually exclusive technically. So they are mutually exclusive. When you add things together, They're going to be mutually exclusive of each other when you use the word or. So the formula sheet, great way to cheat. We're throwing some points for being here. The formula sheet has all the answers right there with when you add things together, a brown or red M&M, which is going to be adding the two values, would be just add the values. They're mutually exclusive. They can't occur at the same time. The probability of not getting a green M&M is the complement. So what's the probability of not getting a green M&M? What's the probability of not green? What's the probability of not green? So we see the probability of green. The probability of not green, great job, John, right there, is 0.90. What is the probability the M&M is striped? Well, that's a weird question. There are no striped M&Ms, so that is 0. Now we're doing it. It says an infinite bag of M&Ms, so this is sampling without replacement. We don't, or whatever, with replacement. It doesn't matter. Rock knows.
It doesn't matter.
So we are going to take, it says right here, suppose you pick 3 M&Ms. So what is the probability they're all orange? Now, when you think about this right here, I wish it let me draw my color. Where's my, is that? No. Really? Oh, the pens are down here now. So when you draw your M&Ms, the first is orange, and the second is orange, and the third is orange. What's the probability they're all orange? The first is orange, and the second is orange, and the third is orange. Notice I said and? It's not like each M&M would impact each other. What is the probability the first is orange and the second is orange? You got it, John. You take 0.1 times 0.1 times 0.1, and that is the probability. So it's going to move the decimal place back. And you're going to get 0.001 right there, I believe. Tell me if I got it wrong. What is the probability of the third one being the first blue? So this one's a little bit weird. You have to think about what's going on. If the third one is the first blue, that means the first one was not blue, the second one was not blue, and the third one was blue. So what is the probability of this? The third M&M being the first blue. So remember I said the first one was not blue, and the second one was not blue, and the third one was blue? So what's the probability of this? Yep, I think so. Great job. Nice job, John, right there. It's going to be the first was not blue, and the second was not blue, and the third is blue. So that's going to be 0.081. Tell me if I got my math wrong. It's 9 times 9 to move the decimal. Because 0.9 times 0.9 times 0.1. There we go right there. So that's the probability of that one. I like these problems. They're fun. What is the probability that none are brown? So, I mean, just think about how to solve that. What am I going to write? The first was what? If none are brown, then it's like, who can do it? I don't want to, I'll write it out more, but what is the probability none are brown? Which I can almost solve in my, yeah, it's like 0.341 or something. Something like that. I should be able to get closer. It's like 0.34. Very close to that. Something like that. So what's the probability none are brown? The first is not brown, and the second is not brown, and the third is not brown. What's the probability none are brown? Who's got it? Here, I'll start writing it out a little bit more. Yep, that's it. The first is not brown, and the second is not brown, and the third is not brown. So it would just be that they're all not brown. So that's the probability right there. And we solve it out. 0.7 times 0.7 times 0.7. And there it is, 0.343. Is that what I said? Very close to it. And then the next one says, what is the probability at least one is green? So either at least one is green or what? So either at least one is green or what? So you're either going to have, it's either the case, which is 1, I'll write it up here. It's either the case that at least one is green, at least one green, or what? You're going to have at least one green M&M. So you look at your M&Ms, and there's either at least one green, which that would be at least one green. This would be at least one green right here. I know there's no purple, it's not yet. And that would be not at least one green. Exactly, and people are already solving it in the chat. It's either the case that there's at least one green or there's no green. So when you rework this by bringing this over to the other side, you get 1 minus no green, which is what you don't want to see, is equal to at least one green. So we have to figure out the probability of no green. The probability of no green, which I know those are blue, but the probability of no green is the first is not green, the second is not green, and the third is not green. So the probability of no green is not green times not green times not green. The probability of not green is 90%. So it's going to be 0.9 times 0.9 times 0.9. It's going to be about 27%, 27, 28% or so when we do the 1 minus. So the probability of not green 3 times is that. And then we do 1 minus, and it's 27%. So there we go. That's the probability of at least one is not green. And we should have done it right, I hope. Do not round, do not round, do not round. We've done it. I was a little worried. That's a tougher problem. Do people feel like they understand this? It's the multiplication rule. It's the addition rule. You want to be able to say it like the first was not green and the second was not green. You want to think about literally picking out M&Ms and what color they are. Probably one of my favorite problems. And if you can do these sorts of problems, you really understand it. Like, I know I have a help video now with it, but these are tougher problems right here. That's tougher. Problem are we going to do now? Which problem are we going to do now? Let's see. Well, someone drop another problem. Kind of. We could do the soda problem. It's one of my favorites. Soda problem. This one, I like this one a lot. It's, if you notice, solve these. Here, I'll put it in the notes. Drop another problem. I'll do this soda problem, then we'll do whatever problem people want next. 38, 33. One of my favorite problems. We've got another 2015. You got it. You got it, Payne. We'll do that one next. You got it. For a sales promotion. And this is just like the other one. I got a bunch of easy multiple choice. We could do those too. Reptar, we could do easy multiple choice with the 5 landlines. We'll do the 5 landlines next. So there's a 6-pack of soda right here. And it wants to know, what is the probability you win something? So the probability of winning something is going to be, as long as I do this right, 2, 3, 4, 5, 6, 1 minus, and there's the answer, and you round down to 3 decimals, and you solve it. We got it. So how'd I do that? Well, when you buy soda, and it's a 6-pack, you will either win something or what? If you buy soda, it's either the case that you win something or what? So one of these things must happen. 100% probability that you will win something or what? You will either win something or what? Or nothing. Win nothing, right? So what can we do? We can rewrite this to figure out the we want to figure out the probability of winning something, which is win at least once. Or what is the probability you win something? It literally says win something, which is win at least once. Same words. So all we do is we just math this over to the other side here, and we get 1 minus win nothing equals win something. So now we have to figure out the probability of win nothing. We have to be like, what is the probability you don't win anything? Well, think, you get your first soda and you open it, and what? What happens? Did you win or lose? Well, your probability of winning, if you win nothing, your probability of winning is equal to 0.26. So when you open that first soda, you don't win. You lost. So what is the probability of losing on every soda? Because you have a 74% probability of losing. So what's the probability on the 6-pack of soda you buy, you lose on every single soda? So you lose and you lose. We could do lose as red right here. So you lose and 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 you lose. What is the probability of winning nothing, which is all 6 are losers? There's your 6-pack right there. Every single soda you lost on. That's it, randomized. The probability is going to be, and we're doing 1 minus it, as the screen goes a little wonky right there. 1 minus the probability of 0.74 to the 6th power. So that's it. That's the answer. The probability of winning something is 1 minus 0.74 to the 6th power. And that, if you solve that, you get the answer, which I got right here. And that solves out mathematically to this right there. There's the answer. Okay, let's do that other landline problem. Okay. Is this it right here? This is 11. So the only thing that's going to change about these, we'll do the other landline one right here. Peyton, tell me yes or no if this is good. I can kind of try to do it with 5 too if you want. We'll wake up eventually. Here we go. So with this one right here, this is good. Good stuff. And I think it's your 51% probability, so the numbers will be very similar to what you have. So we write down, this is the probability of them having no landline. Okay, so it says 51% of households have no landline. So if we write probability of no landline equals to 51%, what are we going to write for this one? What goes mathematically here? Probability of no landline is 51%. What goes mathematically in that second one? Probability of no landline is 51%. I think you're jumping up to the next question. But the first thing right here, I always mark my
Notation,
brother.
brother.
Exactly, John's right there. So the probability of landline is 49%. Just some beginning stuff. You might be already doing the first problem. Good work, Peyton, right there. Oh, I think you even kind of included it. So the probability of not having a landline is 51%. The probability of having a landline is 49%. So now we're going to pick 11 households and look at them. So the first question we're asked officially is going to be, what is the probability that all 11 of them have a landline? Okay, so the first house has a landline, and the second house has a landline, and the third house has a landline. What is the probability each one of the houses has a landline? So we have the probability a house has a landline. What is the probability all 11 houses picked at random have a landline? The first has a landline, and the second has a landline, and the third. And you hear that and word right there? And? You got it, John. It's just going to be 0.49 times 0.49 times 0.49 repeated until we've raised it to the 11th power by multiplying it multiple times. So that's the probability all 11 houses have a landline. What is the probability that at least one of them does not have a landline? You have to be very careful. We're asking, what is the probability at least one does not have a landline? And actually, I think it is that easy. I overthought it. So either at least one does not, at least one does not have it, or what? So either at least one of these houses does not have a landline, or what? Or what? Either at least one does not have a landline, or what? Either at least one does not have a landline, or they all have. And we just figured all have out. We just figured out the probability they all have landlines. So what's the math? We literally just figured out the probability they all have landlines. So what's the answer to what's the probability at least one doesn't have a landline? Because either they all have landlines or at least one doesn't have a landline. That's it. You subtract. Yeah, the next one is simply the complement of this because it's either the case they all have landlines or at least one doesn't have a landline. So that'll be the next one. And then the last question right here says, what is the probability that at least one of them does have a landline? Now notice how this is a flip. So what would it be? Either at least one has a landline or what? So the math is going to flip here a little bit because either at least one has a landline, like maybe one of them has a landline, two of them has a landline, three of them have a landline, 4 or 5, at least one has a landline, or what? Either at least one has a landline or what? And John's got the math, or none of them have landlines. So you would do 1 minus none have landlines. So you would do 1 minus none have landlines. So there it is right there. Or not, like either at least, and so you just be like, what is the probability? We're trying to find for the third one here, at least one has, or none have. And the probability of none having is this. Because that's all 11 don't have landlines. So that's the probability one doesn't have a landline is 0.51. The probability all 11 don't have landlines is 0.51 to the 11th. And they subtract that. The complement of none having landlines is at least one has a landline. Does this, Payne, did this help out a good bit? And I think your numbers are just 5 for it because you're doing 5 houses. So it's, if the numbers are the same, should be good to go. And we should have done the math correctly. Let's see right here. So that all 11 have landlines. So the probability of a landline is 0.49, right? I check my math. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh my gosh. So this is 3, 9. I think it's that. I don't think it rounds. It doesn't round. And then what's the probability? The next one does minus this. So we just do 1 minus, which we can kind of figure it out ourselves. And then the last one is very similar. It's going to be similar to that, but it's going to be a little bit... it's going to be like... I'm taking a guess at it. Bless you, Charlie. I'm taking a guess. Okay, if I got that right, that'd be amazing, but I don't think I'm going to get it right. 151... 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then 1 minus. Oh, I did. Oh, there we go. Oh, that's nice. And there's the 3, 9. That was close-ish. So, and that should do it. There we go. Too many decimals. Oh, too many decimals. Look at all those crazy decimals. You got to continue not mess up. Too many decimals. Which problem we doing next? Multiple choice. Should we do some easy multiple choice? Let's do easy multiple choice. Just that way it looks like we did a lot more. And I do have videos for pretty much everything. If you check old videos. Let's say easy multiple choice. All right, easy multiple. Watch me get this one. I think I could get wrong. Easy multiple choice. You're welcome, Peyton. And great work. 5,000 points right there. Okay. Flipping coin is said to generally be random or whatever. Explain what random means. Random means you would kind of know, and Reptar's got this one right here, good Reptar. It means a fair coin will flip this. It won't do exactly. A fair coin's not going to do exactly. It means for each outcome, you cannot predict it. No, that's law of averages. You can't predict it if previous things are known. That's not random at all. This one's wrong because you can't predict it knowing previous events. That's not what you would do. Things don't average out. And it's not going to predict exactly 50 heads, 50 tails. In the long run, law of large numbers, it's going to be approximately in the long run. Of course, theoretically, it does go exactly towards 50%, but it doesn't say the theoretical long run. Funding schools, is that another short one? We'll do some short ones here, and then we'll... I'm trying to remember which one that is. Funding many schools. Let me see if I can find that one. If it's a short one, we'll just do it really quick. For some reason, my brain's like, what is that one again? I don't remember this one. Oh, here it is. Oh, good. It's multiple choice. Thank you, Reptar. Good answer. Good question, Reptar. Funding many schools comes from tax based on assessed values of stuff. People's homes are assessed if they have extra features such as multiple bedrooms, hot tubs. Why do you want to? I don't know. Okay. Put it outside. No, Veronica, you're fine. Drop a question in the chat. We'll do it. Assessment records on a certain school district indicates 31% of homes have a multiple bathrooms, 4% have hot tubs. The addition rule would suggest that 35% have a hot tub and multiple bathrooms. Is that the way the addition rule works? Yes or no? Don't even read their answers. I know what we're looking for in the answer. Can you just be like, well, 4% of homes have hot tubs? I guess like a jacuzzi hot tub, right? 4% of homes, no, that's different. They're talking like an actual hot tub, I think. 4% of homes have hot... No, why does it not work this way? What's wrong with adding up 4% and 31%? No, I think you're going to say it. Well, we can say 4% of homes have a hot tub or multiple bathrooms. You can do that. You can say that 4% of homes have a hot tub or multiple bathrooms. Don't read their answers. Because then if you know what you're looking for, then it makes it very easy to find the answer. Peyton's getting into it right here. Peyton's right. They're not disjoint. Because the addition rule requires that things are disjoint. So you can't... To add these probabilities... It has to be that if a home has a hot tub, it can't have multiple bathrooms, which is not the way things work. It doesn't work that way.
It doesn't matter.
So since they're not disjoint, you can't simply just add them. So the sum of the probabilities, no. I'm looking for where it says disjoint, not independent. There we go. The events are not disjoint. There it is, which is the same thing as mutually exclusive, which is a requirement. So if you know what word you're looking for, you can just look for disjoint, which is the same thing as mutually exclusive. Like, to add things together, remember we showed the review sheet, which you do get for the test. You get the note sheet. It literally says right here, mutually exclusive, which is the same thing as disjoint for the addition rule when you add together two probabilities. Okay, let's knock out a few more multiple choice ones real quick. Rolling a fair dice or whatever is supposed to generate a number 1 through 6. What random means in this context. I don't remember this question. That in the long run, a fair dice will produce roughly equal amounts of 1 through 6, but for each roll, 1 through 6 is equally likely. That sounds right. There you go. After rolling doubles on a pair of dice, your friend claims, I can't get doubles 4 times in a row. That is the law of averages. Your friend is using the law of averages, which is not a law. It's a fallacy to say, gosh, look at all these things that have happened. It makes it less likely now. No. It would be that each dice roll is independent. There is no law of averages. 3 dice rolls do not affect the 4th dice roll. Whatever happens on that trial is independent of past things. There's no law of averages. The law of averages is not true. There's no law of averages. It's not real. It's just a fake thing. The property which states that for independent trials, as the number of trial increases, the long-run frequency of an outcome gets closer to the true probability of an event. That's going to be the law of large numbers right there. So that's the law of large numbers. Empirical probability is probably talking about the empirical rule. Sample space is everything that could occur. Law of large numbers. Nice job right there. 3 points, Logan. Law of large numbers states that over the long-run trials, you'll see the true probability of an event. That's an easy one right there. We've done a lot. Drop another question. We have time for at least maybe 1 or 2 more. We could do another harder one. The Red Cross one is very similar. And what other ones do you have? Drop them in the chat. We've done a lot of it. These are easy. So, go over Canvas questions. Yeah, you want to do the Canvas quiz? Canvas content quiz? Let me see it. Let's do the Canvas content quiz. Be a good way to end. Canvas content quiz. Oh, did you already do it? Is it 0.35? Is not black. So, wait, no, there's not that many shirts in here, is there? Oh, no, there it is. There's 20 shirts. So not black is going to be 0.55. Did we just do this one? Oh, wait. Is red. 7 red shirts. Not black. 9 black shirts. Blue. I did blue. Oh, my gosh. I can't do not black. There we go. I saw the B, and I misread it, apparently. And then this one's very similar. And then we'll do Canvas content. How many songs? This is using X over N. So you want to note right here, this is the number of occurrences over the number of total. 3, 8, 5. So that's 16. Probability a rap song is played. So that's 50%. 8 over 16. Probability not country is 11 over 16. That's a fun one. I can do that. I got this. My brain's saying 62.5, but my head's saying no. My gosh. 5/18. I'll just cheat. 68.75. That should be right. There we go. Okay. And let's go check out that Canvas content here. What do we got coming up? Canvas content. Oh, chapter 12 and 10. Do this Friday. Okay, we'll end here with some Canvas content. Okay. And then I'll grab a drink. And I'll take my walk to class. Okay, is this number 7? Oh, do you want to do number 7? We got number 6 up right now. Should we do number 7 instead? 6 or 7? Say it in the chat. Randomized gets the biggest vote. 6 or 7? What should we do? 7? Well, let's do number 7. Okay. Can I go back? 6. Oh, no, don't do that to me. No. What did I do to myself? Okay. I didn't. Oh, my gosh. 6, 7. We're doing number 7 now if people don't want. Like, whatever. We're doing Canvas content number 7. Wait. Oh, there it is. Number 7. Okay, here we go. Okay. All right, Canvas content, chapter 13, or Canvas content number 7. Okay. So let's go ahead and preview it, and let's do it. This is going to cover stuff we haven't totally covered. We'll cover it on Thursday. So this first one, and this is kind of what I was asking in class today, was about the success-failure condition. What 3 things do you need for the success-failure condition? We covered this at the very end of class. Here's the notes. So what three things do you need for the success failure condition? What three things do you need for the success failure condition? So take a look at the notes. There's the success failure condition. What three things do you need? I mean, basically says it. And then we got the notes beside it right here. Yep. So, well, that's the 10% condition, Peyton. That's the less than 10% condition, which is condition 2, which we got previous notes right here on checking the less than 10% condition. And and we don't divide though. Randomized, good answers randomized. That's why I love going over this. We don't divide them. We just see that NP, like these are two separate things. Like NP and NQ are both greater than or equal to 10. So you don't divide them. You just make sure that there's at least 10 successes and at least 10 failures. So if we go look at this problem right here, what is N for this problem? What is N? We're doing great. Just answer as many questions as you can. What is N for? No worries. What is N for this problem? Little tricky. This question can be answered correctly in a lot of wrong ways. What is N for this problem? It is that correct, because that says sample. N is sample size. So the sample is 500. What is, and I wish I want to change this. It should say if the defect rate is 3%. I wish it said that. So that means P is equal to 0.03. What is Q equal to now? What is Q equal to? I wish it just said the defect, because you'd be like, what if the defect rate is like 99%? Well, then our company's shut down. We got bigger problems than running this. There is a theoretical way to break this problem. You're correct. It is 0.97. So the complement is 0.97. So how many expected successes do we have? What are the expected successes out of 500? We just solve it. You plug in the numbers. You plug in the numbers. Well, it's purely subjective what a success and failure is. A success right now is a defect, but success just means the thing you're interested in looking at. Logan, kind of, whichever way you do the math is fine. It really doesn't matter. But the technical way this math is set up right now is 500 times 0.03 equals 15. And then 500 times... so it really doesn't matter, because you'll get the right answers either way. So do we pass the condition, yes or no? Do we pass? No L's. 5,000 points, Logan. Success is just the percent of time the thing you view is occurring. It doesn't mean a good or bad thing. There's no value to it. It's just, did we observe the thing? We pass it because we have at least 10 successes, at least 10 failures. The three conditions must be met in order to calculate p hat, yes or no? Type yes or no in the chat. The three conditions must be met in order to calculate p hat. We must meet the three conditions to calculate p hat. No. Nope. We have to meet and I probably didn't stress this enough today. No, and a lot of people get this wrong. This is a very commonly missed. It's almost like this is one of those ones that appears on the test. So you're here and you know it now. Well, how do we calculate p hat? What is the mathematical formula for p hat? I'll show it to you. But what is the mathematical formula for p hat? What is the mathematical formulas for p hat? Like, tell me the math for p hat from today's slides. I'll show you to you in a second, but just take a guess. It's x over n. That's all it is. So remember when we said like 12, not 12 of your friends, like, 12 of your 50 friends got mint chocolate chip ice cream. When I said 12 of your 50 friends got mint chocolate chip ice cream, did you have to do any, and great job Logan there too. There's no conditions for calculating p hat. It's just what percent out of a sample. 12 of your friends got mint chocolate chip ice cream out of the 50. So that's all it is. P hat is just sample proportion. The reason we do the conditions is to see if the data is normally distributed. I didn't make that really clear today, but I'll try to stress it next time, that the conditions are used to see if the data follows the normal. If you don't meet the conditions, you can't use the normal. So the conditions are checked to see if you can do the normal. You don't need the conditions to calculate the sample mean or the sample proportion. That's not what the conditions are there for. The conditions are there to see if you can use the normal distribution. If you fail the conditions, you should not be using the normal for your data. So this is false. You do not need to check conditions for p-hat. You check them to see if the data is normal. Success failure states that your measurement must be binary, either a success or failure. True or false? Just don't worry, we're just practicing. True or false? The condition states, the success failure condition states that it must be binary. True or false? This was covered today also. True or false? If you get it wrong, it's just practice and you'll remember. Is this what the success failure condition says? The answer is false. The success failure condition states you must have at least 10 successes, at least 10 failures, checked by NP&Q greater than or equal to 10. So there it is right there. This is what it states. The sample size has to be big enough so that both NP and NQ are at least 10, such that NP is greater than 10 and NQ is greater than 10. This is NQ right there because 1 minus P is Q. And yeah, so don't worry. Good answers in the chat. Good practice. It is false. The success failure condition doesn't state it has to be binary. It still has to kind of be binary. I'll tell you the next few right here because we haven't covered the second part of this yet. According to the central limit theorem, which of the following will happen to the sampling distribution sample mean as the sample size increases? The distribution will get tighter and it'll get more normal. So it gets more normal. That'll be covered with the large enough n condition. The conditions for the sampling distribution and the sample mean, when you know the true mean are, and I just said it, random, 10%, and large enough condition. Success failure is for proportions, and I'll try to make that very clear next class. We did talk about it this class, but a lot of people get confused because they're like, wait, when is it large enough n? When is it success failure? Success failure is for proportions. We'll do another version of this. True or false? We need the three conditions met to calculate p-hat. True or false? To calculate p-hat, which is x over n, you need to meet some conditions. The random 10%, that's false. You don't need, it's just x over n. You calculate it. All things being equal, the smaller the standard, all things being equal, the larger the sample size, the smaller the standard deviation. So here's the math behind this. It's saying if you have a larger sample size, so P times Q over N square root, the standard deviation gets smaller. True or false? Yeah, I think people are saying. Yeah, because if this gets bigger, this gets smaller. Does that make... Do you see... Who sees it mathematically now? Mathematically speaking, if you get a larger sample size, which is down here, n, then the standard deviation is going to... Because you're dividing by n. So mathematically, it makes sense. So, and it's like, someone could be like, well, what if p is different? It's like, well, everything else basically the same. If you're not changing other things, then larger samples lead to smaller standard deviations. That's true. We did this one before. This was true. Central limit theorem relates to which of the following conditions? The nearly normal, and that actually was kind of covered in the last one, that the data becomes more normal and tighter. So it's related to the nearly normal condition, which is the normalization of data. Conditions for the sample distribution sample mean are random, 10%, and large enough n, which will be covered in next class, large enough n. We'll try to see if we get any other versions of it. Have people gotten hundreds already? Does not state that it needs to be binary. It says we need at least 10 successes, at least 10 failures. We do not need to meet conditions. If we get a larger sample size, the central limit relates to data being normal. According to central limit theorem, which of the following happens, the distribution as sample size increases, it gets more normal, part of the central limit theorem. Data gets more normalized. 10 out of 10, nice. Yeah, I hope you'll always get 10 out. What did I... Well, now I can't see it. I must have missed... I'm literally going to go review the tape on that. 2 seconds. I'm not going to miss a question on that and see what I didn't get wrong. Success failure condition. Central limit theorem, which of the following will happen to the same end? Failures, but portion. A lot of failures for proportions. We'll do another version of this. True or false? We need hat. We need... Let me see what I got wrong. Confused on the binary question. It's like the condition either... Well, it's not... No, it's saying like the data has to be binary. That's not what the condition states. The condition doesn't state your data has to be binary. The condition states that you must have at least 10 conditions, at least 10 failures. You could say like a prerequisite for it is binary data that's categorical, but the condition itself is not that data needs to be binary. Oh, no. Well, it's going to be open again tomorrow, John. Swing by some in-person office hours if you want. We can review it. We can do some work. In-person office hours tomorrow. Swing by. We'll get some work on it. Chapter 12 is a tough quiz. Probabilities, a lot of math. The three conditions for sampling distribution must be met in order to calculate p hat. That's false.
P hat. True or false?
Let's see where I made a mistake on this. I did it quickly. So that's false. Come on, Brian. Start doing the quiz. It's false. All other things being equal, the larger sample size, the smaller standard deviation. That is true. Oh, this is the... Gosh, we've done so many versions. This is the version where I explained everything. No, I missed. The central limit theorem relates... Oh, I must have clicked less normal. Oh, I did click less normal. They should be, yeah. Let me do that right now, Veronica. So I don't forget. I could get home and I'll be tired. We have a big event today. So let me do that. Good questions, everyone. Great office hours. Are people feeling a little bit better? Let me go fix this right now. It's so crazy how you have to fix stuff. Like, it's very counterintuitive. Good to hear. Due tomorrow. It's crazy everything was down yesterday. Save and assign. Okay, so that should be the one of the two. I just changed one of the two. I did the homework. Okay. You're welcome. I think it's fair since you kind of lost today. I know it's kind of a bummer because maybe there's probably someone who's like, with your cat. Oh, you're welcome. You're welcome, John. I'm glad these are... Thank you, everyone, for showing up. It really means a lot to me that when we have a good amount of people here practicing. Today's office hours, we got a lot done. You can see right here, everything covered. We covered some of the hardest questions. We'll do some of the harder ones again tomorrow. So swing by. I'm going to go get some drink right here and got my protein bar. Till then, bye for now, everyone. Bye.